Hello there, Mr. Sutton here, bringing you the AB Calculus 4-5 Extra Practice Number 4 solutions on points of inflection. To find points of inflection on this problem, we have to first find the second derivative and see where that changes sign. So let's start with the first derivative. That's going to be negative 3x squared plus 6x, and then that 5 is just gone. Now for the second derivative, that'll be negative 6x plus 6. And we need to figure out critical values of this and do a little sign analysis. So if I set this equal to 0 and subtract 6 and divide by negative 6, I see that I have a critical value at x equals 1. So let me put that on a f double prime number line here. Here's 1, and let's test around that. So something to the left of 1, let's try 0. Plugging that into my f double prime formula, that's just going to be 0 plus 6, which is a positive. And then testing something bigger than 1, such as 2. If I plug that in here, that's going to be negative 12 plus 6, which is a negative. So I see here that f double prime changes sign at x equals 1. Therefore, f has a point of inflection at x equals 1. To find points of inflection for this function, we're going to try to see where f double prime is changing sign. So first we have to find f double prime, and before that even f prime. And to find f prime, it looks like we're going to need the quotient rule, u prime v minus uv prime over v squared. So let's set up a box and ribbon to organize this. So I've got a numerator of x squared. I'm going to call that negative x squared just to take care of that negative in the early going. And denominator is going to be 4x minus 4. Derivatives, we've got negative 2x and 4. Multiplying this out with the ribbon now, so I've got a big fraction going on here. We're going to have negative 2x, and I'm going to just distribute that to the 4x minus 4 right away. So this is going to be negative 8x squared plus 8x. And then we're going back the other way, minus negative x squared times 4. So that's going to be plus 4x squared. And that's all going to be over v squared, which in this case is going to be 4x minus 4 quantity squared. All right, so I'm going to simplify this a little bit because I'm about to take another derivative. So let's make my life a little bit easier. Negative 8x squared and 4x squared, that can simplify to just negative 4x squared. So I'll put that in there. All right, so this is my first derivative. Now to get the second derivative, I'm going to go ahead and use another quotient rule. So box and ribbon time again. This time I've got 8x minus 4x squared as my numerator, and 4x minus 4 quantity squared as the denominator. So for my derivative this time around, for my u prime down here, I've got 8 minus, this will be 8x. And over here, I'm going to need to use the chain rule. So this is going to be 2 parentheses 4x minus 4 times a tail of 4. So if I simplify that a little bit and I multiply this 2 here with the tail of 4, that's going to be an 8 times 4x minus 4. All right, let's multiply this out now. I'm going to have 8 minus 8x times 4x minus 4 quantity squared. And I'm not going to simplify things just yet. I think I see a lot of these 4x minus 4s, so I think I might be able to cancel these, but we'll have to see. Let's keep going. So now I'm going to have minus parentheses this stuff times 8 times 4x minus 4. And then finally I'm dividing by 4x minus 4 squared, so that's going to be 4th power for that stuff down there. And looking at what I've got here, I do have a whole bunch of these 4x minus 4s. I've got at least one 4x minus 4 in each of these terms and the denominator. So I'm going to cancel out one of those 4x minus 4s. That's going to give me 8 minus 8x times 4x minus 4 to the first power over here. Over in this second term, this 4x minus 4 is just gone completely. And down here, this is going to be third power now. So 8x minus 8, first power over here, that's gone. And third power down below. All right, we're going to simplify a little bit more because at some point we have to figure out where this thing is either 0 or undefined. And that's going to be easier if I have fewer things floating around. So I'm going to FOIL out these first two parentheses. So that's going to give me 32x. And then we're going to have negative 32 minus 32x squared. And then the last is going to give me plus 32x. And then distributing this negative 8, I've got negative 64x plus 32x squared. Combining like terms, let's see here. I've got a negative 32x squared, a positive 32x squared. Those are canceling. I have a 32x, another 32x, that's 64x, minus 64x. Those cancel. So all that's left now, it looks like, is just this negative 32. Okay, well, this fraction here, since I have a constant in the numerator, this cannot equal 0, so I'm not going to get any critical values out of that. However, I do have a value where f double prime does not exist if x equals 1, because 4 times 1 minus 4 would zero out the denominator. So this might be a critical value where I have a point of inflection. However, if you look back at the original equation, I mean before we even bother doing sign analysis here, if you look at the original equation, 1 is going to zero out the original denominator. So because f of 1 does not exist, you can't have a point of inflection at x equals 1 because, quite simply, you don't have a point that is on the graph. So because there is no point of inflection at this only critical value that we found, there is no point of inflection at all for this function. After all that, to find points of inflection for f of x on this problem, I want to figure out where f double prime, the second derivative, is changing sign. So let me start with the first and then the second derivative, and we'll go from there. F prime on this one, that's going to be negative 4x cubed plus 4x. And we need to go one more derivative now to talk about points of inflection. So f double prime, that's going to be negative 12x squared plus 4. And at this point, I need to set this equal to 0 and find some critical values to do a little sign analysis. So let's see here. If I subtract 4, what's a good way? Should I move things over here? Should I factor? Let me just move this 4 over here and divide by negative 12. So that's going to be positive 1/3 that x squared equals. And then I'll just square root both sides. So that's going to be plus or minus square root of 1/3, which you could also call radical 3 over 3 if you wanted to. So let's put those on a f double prime number line. We have negative radical 1/3 and positive radical 1/3. And testing something to the left of negative radical 1/3, how about negative 1? So I'm just going to plug that into this f double prime formula over here. So if I plug in negative 1, that's going to be negative 12 times 1, so negative 12 plus 4, which comes out to a negative. And a number between these critical values, 0 is a good one. That would give me 0 plus 4, which is a positive. And we'll test out 1, because that's to the right of radical 1/3. That's, again, negative 12 plus 4, which is a negative. Now I notice here that f double prime is changing sign at both positive and negative radical 1/3. Therefore, f has points of inflection at both of those x values. To find points of inflection on this equation, I'm going to see what the second derivative is doing, looking for sign changes. So let me start with the first derivative. F prime, that's going to be negative x, using the power rule here, negative x plus 4. And then f double prime is just going to be negative 1. Now, before we even bother trying with sign analysis, I mean, this is a constant. It means that f double prime is always going to be negative, which even more importantly than that, means f double prime never changes sign. If you don't have a sign change in f double prime, you do not have any points of inflection. For this one, I'm trying to find all the inflection points for tan of x between negative pi and positive pi. So for inflection points, I need to look at where the second derivative is changing sign. And also important, the point has to actually exist on the original graph, which is especially important for tan because we know there are some places where tan is not defined on this interval, specifically at pi over 2 and negative pi over 2. But we'll get there when we get there. Let's find the second derivative. Before we do that, let's find the first derivative. That would be secant squared of x. And now the second derivative, I'm going to need a chain rule on this one. That'll be 2 times secant times the derivative of secant, which is secant tangent. So 2 times secant and then Secant tangent is that chain, that tail. I'm going to simplify this a little bit so that I can find critical values more easily. I can think of this as 1 over cosine, 1 over cosine, and sine over cosine. That gives me a grand total of 2 sine of x over cosine cubed of x if I multiply all those cosines in the denominator together. And I'm trying to figure out where this thing is either 0 or undefined. Let's talk about 0 first. So for that, I need the numerator to be 0. So 2 sine of x is going to be 0 wherever sine of x is 0. That's going to be where the y value is 0 on the unit circle. So on the interval from negative pi to positive pi, that's going to happen at negative pi, at 0, so basically the two sides of the x-axis, and also at positive pi, which is pretty much the same in terms of how it behaves as negative pi. So that's 3 critical values, but 2 of them are endpoints anyway, so it's really 0 that gives us that extra spot. Now let's talk about where this tan function is undefined, or at least this tan second derivative is undefined. F double prime does not exist wherever cosine equals 0, and that happens at negative pi over 2 and positive pi over 2. Basically, if you are on the y-axis at negative or positive 90, you have a cosine value of 0, which zeroes out the whole denominator. All right, so let's set up an f double prime number line for this. And for endpoints, we have negative and positive pi. And in between, we have some critical values. We have negative pi over 2. We've got 0 is the next one. And positive pi over 2 is the last one in there. And let's test something from each of these 4 intervals. So from negative pi to negative pi over 2, that's basically the third quadrant. So if you plug something from the third quadrant into, well, this is the version of f double prime I'm going to be looking at here. So let's see what's going on there. In the third quadrant, sine is negative. Cosine is negative because you're to the left of the y-axis and below the x-axis. So that is 4 negatives, but that's going to give us a positive. Next, between negative pi over 2 and 0, well, this is going to be the fourth quadrant. In the fourth quadrant, sine is negative, cosine's positive, so that's 1 negative, which makes this whole thing negative. Between 0 and pi over 2, that's the first quadrant. In the first quadrant, everything is positive, so that's a positive result overall. And between pi over 2 and pi, that's the second quadrant, where sine is positive but cosine is negative. So that's 3 negatives, giving me a negative overall. So looking for sign changes here, there is one other thing actually we have to be careful of, because I see 1, 2, 3 places where f double prime appears to be changing sign. However, 2 of these don't count, because we said in the beginning, tangent is not defined at negative pi over 2 or positive pi over 2, because tan is the angle, is the slope of your angle, and at these 2 angles you have a perfectly vertical slope, which is to say your slope does not exist. So f of plus or minus radical 2 does not exist, so there's no point of inflection there. However, 0, tan of 0 does exist, and f double prime does change sign at x equals 0. Therefore, f of x, tangent, has a point of inflection at x equals 0. And if you look at the graph of tangent, you'll see that that is visually the case. For this problem, I'm trying to find points of inflection for this quintic polynomial. So for that, I need to see where the second derivative is changing sign. Let's get the second derivative, and before that even, let's get the first derivative. So we've got negative 5x to the fourth, just using the power rule here, plus 9x squared. And we need one more derivative, so f double prime, that's going to be negative 20x cubed plus 18x. And at this point, we're going to set this equal to 0 and look for critical values. So in solving for this, I can factor out, it looks like a 2 and an x. Let me make it a negative 2x. That'll leave me with 10x squared minus 9 inside. So I see that I'm going to have critical values if x equals, for this factor here, 0, or if I add 9, divide by 10, and square root both sides, radical 9 over 10, plus or minus. So that's 3 critical values for me to try out on my f double prime number line here. We've got negative radical 9/10, 0, and positive radical 9/10. Let's test something in each of these intervals now. Something to the left of negative radical 9/10, how about negative 1? It's a little bit to the left, right? Because negative radical 10/10 would have been negative 1. So plugging negative 1 in, and I'm going to use this factored version now of f double prime. That's going to give me a positive, and let's see here. This is basically 10 minus 9, so that's another positive. Overall, positive result. Now, how about something between negative radical 9/10 and 0? Well, how about negative 1/10? I'm pretty sure that's between. So that gives me a positive out here. And in here, this is going to basically be 10 times, let's see, if we're squaring 1/10, that's going to be 1/100th. That's going to be a small number. Subtracting 9 is going to give me a negative in there. So that's going to give me, let's see, a negative times a positive is a negative. Now between 0 and 1/10, we've got a negative out here, and again, we're going to get a negative inside here, so that's a positive overall. Finally, 1 is bigger than radical 9/10. Plugging in 1, that's a negative out here, a positive inside the parentheses, so negative overall result. Now, all of these x values exist for the original function because it's a polynomial. I notice that f double prime is changing sign at 0 and also at these 2 radical 9/10 at all of these, 3 different spots. That means that f itself has points of inflection at all 3 of these x values.